We share the interest in 2D materials, and also, like AtoCube, we share the interest with measuring them in combined different methods. So that's the thing. And 2D materials particularly amenable to combine multiple measurement together and in what we call in a device platform that apply a lot of these traditional material analysis techniques. Of course, that's one part is because 2D material pretty much everything is on the surface. That could be bad, but that could be protected. That could be a good thing when you bring all these surface science, microscopy, spectroscopy, that in conventional bulk material, it almost require separate expertise to do them. But when you're dealing with 2D material, it's much easier to do them together. In fact, these days, as we heard, many measurements, instrument measurements done today in 2D materials are combined, for example, optical measurements with some gated devices, so it's very common now. So it's very tunable by applying a gate or flowing current and so on and so forth. So this is the thing. So we've been building transistor type devices, but subject these to optical spectroscopy or give collaborators to do RPES, and even more recently, or even early days, combining with some scanning probe type of microscopy or spectroscopy. So that's I think that's, of course, today when we order things from AtoCube, we always ask for many, many things together in probe. We always have many electrodes, even for scanning probe and optical probe. Okay, so I will give example from graphene, mostly twisted graphene, but some early example, maybe just from graphene. So we make examples, some sample with a CVD, growing these twisted bilayer graphene back in early days. But of course, we also do exfoliation, tear stacking, as we heard. Last part talk, I show some more recent results. These twisted insulating antiferromagnets, layered antiferromagnet that we heard yesterday, chromium iodide, for example, built by this stacking approach. And the examples of, I mentioned that you can subject these devices to many type of measurements, RPES, scanning probe, like a graphene, optical, Raman, or for the magnetic material, for example, magnetic optical curl measurements. All of these can show very interesting behavior. You'll learn a lot more by tuning gate voltage, current density, so on and so forth. Okay, so just in very early days, this is not yet twisted, this is just graphene. Former PhD student, now Professor Harugui in California, flow current on a suspended graphene and heat up that middle. It was able to read temperature by Raman spectrum. So very simple technique. You can back out the thermal conductivity of graphene. So very simple application, combining electrical devices and Raman. Here's another example. By applying a voltage, here the gate voltage, tuning current density, you see the typical graphene Raman spectrum shift in interesting ways. These actually allow you to pull out electron-phonon coupling parameter. And this particular example is actually done on disordered graphene with a tunable disorder introduced by irradiation electron beam. And you see the electron-phonon coupling parameter actually can be changed by the disorder in a way. That's an interesting way. And for Raman expert, this also allows you to question some of the usual convention, how people extract from disorder-induced peak with, say, there's a graphene G-phonon. The ratio usually is treated as some kind of domain size, but this is actually clearly dependent on current density, gate voltage. Okay, so here's another pretty early example doing something like AFM, but here's an interesting AFM tip, a conducting nanowire wrapped with an insulator dielectric, scanning on graphene transistor again. By the way, at that time, the former postdoc, Romana, did this nano broom just cleaning with quantum FM. I think this is a very common thing to do. You need to do this before any type of the clean measurements, let's say in scanning probe. But more interestingly, when you gate graphene near the charge neutral point, and you apply voltage on this nanowire tip. So this is a scanning little top gate, and then you monitor the transport in graphene. When you scan this little top gate, you can see very inhomogeneous response, spatial inhomogeneous response when it's near the Dirac point, where it's not so much away from Dirac point. So this scanning gate microscopy reveals the charge puddles clearly formed near the charge neutral point. One of interesting calibration is that actually this well-controlled top gate allows you to show even locally you remove 1 electron from graphene at room temperature. In this moderate quality graphene actually change its resistance by quite a measurable parameter. So graphene is a good charge sensor. Okay. All right, so now let's look at some of the earlier twisted bilayer graphene. We synthesized actually by CVD almost more than 10 years ago. The nice thing about in one growth, you can get hundreds of these twisted bilayer graphene, whereas you want your student graduate faster. If you do this stacking exfoliation, maybe take years. So it's good for study so this is a collaboration we did with the GFA in Iowa State. Look at these stone measured plasmons imaging for many of these samples at different twist angles. No, I'm not stone expert, but I can see when your angle is, the response can strongly depend on angle. In fact, the wavelengths become much longer when you approach these small angle, match angle region, and this relate to these, your band start to collapse, Fermi velocity start to collapse, so on and so forth. Okay, back to a bit larger twist angle. These are earlier micro RPS measurement. I'll say more about that later. That time down with the Yong in Oxford. And you see this nice Van Hove singularity form between two twisted Dirac cones. And one of the interesting signature of this, you can show up in optical Raman spectra. So one reason for this one, we use a larger twist angle is because the laser of a Raman measurement here is 532 nanometer. We want that energy to match between the separation between two Van Hove singularities. They are these ones here. And there's a well-known phenomenon that when this resonance occurs, you have a very gigantic enhancement of the Raman peak, for example, this G phonon peak. However, when you have a twisted bilayer graphene, in this particular case, we build a sort of a ionic top gate. When you apply this top gate, you can actually again, this is a large twist angle. The two layers are very weakly coupled. You can actually shift the two Dirac cone, offset them by a variable amount, and you almost introduce a phenomenon like driving from direct transition into resonance to some kind of indirect transition, even though this is still relatively gapless. So you suppress this resonance-enhanced phonon. In fact, it splits into two G-peak, one for each top and bottom layer graphene. So there's a lot of interesting electron phonon coupling physics you can learn by these gated Raman mesh on twisted bilayer graphene. So now, back to the smart twist angle. So I want to advertise recent work from my colleague in Aarhus, Søren Ustrup, who has set up a nice nano macro RPS in-house in Aarhus in the basement of the physics department. So very nice, which by the way is open to users. So this is some of the very nice results recently just posted. Look at small twist angle, in fact, near-magic angle, both the twisted bilayer graphene and twisted double bilayer graphene between two Bernal bilayer graphene. And by applying, changing the carrier density, first of all, you see this flat band formation in these systems. But most interestingly, by changing the occupation, band filling, you can see the bandwidth, are being modulated very substantially, as well as a gap between these bands and other bands. So this is obviously a very strong signature of strong correlation physics. We change the occupation, you actually change the entire band structure, bandwidth, so on and so forth. The matter is actually quite different, somewhat interestingly, between the twisted bilayer and twisted double bilayer, which is even more kind of richer. So this is, for more details, you can read. This is the earlier kind of methodology paper, but main results in this preprint. All right, so again, another kind of facility set up over the last few years. This is the one reason we spent time in this part of Atlantic. So we have this this facility can do low temperature STM, but not so much traditional STM on materials of thin film, but we want to measure device. So this helium-3 strong field STM located also in the basement of the Aarhus next to a synchrotron, in fact, can measure a device. Usually, you want, it's not, you don't, these two flakes sitting on the silicon oxide wafer, if you not really approach a tip, you'll crash the tip, right? So you have to develop some methodology, for example, doing far distance capacitance search to guide the tip using these lithography pattern kind of tip guide to walk the tip to a 2D material. So this now, we can routinely find these various tips, various flakes, perform these scanning probe measurements, really as a nanoscale transport device. We want to look at devices. So here are some examples. You can find a twisted graphene on graphite, a nice Moire pattern at some interesting Landau level developed at high magnetic field. These we can measure superconductors, now been selenite, although this is a very thick flake. In field, you see these vortices, a vortex ladder in this case. One of our major interests is to look at actual devices. So this is a device, it's a hybrid between topological insulator and superconductor with some nanostructures that trap vortices. And usually, again, STM doesn't like non-flat surface. So this surface is not only a small flake on the substrate, but it has a lot of these electrodes, nanostructure on there, so it's not flat. But nonetheless, you can develop a scheme to guide the tip into one of these so-called hole and to see how superconductivity is, learn more about proximity and superconductivity. Of course, one of the motivation here is to try to find signature of Majorana, which we don't yet have any convincing signature, but this is also a good tool to study things like Josephson junction that we heard yesterday. Maybe those quantum material can be subject to these kind of atomic scale probes. Okay, so switch the gear. So much about charge-based interesting materials, or charge physics. But now let's talk about the spin physics in the insulator. So there's no charge, mobile charge at least. So these are measurements on some of the 2D magnets we heard yesterday. And now the measurements is based on optical curl effect, which you can measure micron-sized flakes, which will be, for these flakes will be instrument flake with different measure in other methods, the bulk methods or transport. Nonetheless, so in this particular curl setup, it's a polar MOC, so it's sensitive to the perpendicular direction magnetization, okay? So this is iconic results reproducing the Sheldon's 2017 work, calibrating this on chromium iodide. So this is material I'm going to spend the next few minutes. So chromium iodide, as we heard yesterday, in the model layer, it's a ferromagnet, right? Each layer is polarized vertically. But it's an interlayer antiferromagnet coupled. So bilayer, it does not have a hysteresis loop. It's actually layer antiferromagnet. When you go to 3-layer, it's a ferrimagnet. So basically have a hysteresis loop again, so on and so forth. But this is a measure in the natural chromium iodide, which has its usual stacking, okay, monocular stacking. When you twist them, things change very dramatically. So this is the main. So again, before that, I guess we've seen. So the story is you stack these bilayer. Each of it is antiferromagnet, so there's no magnetization. So there should be no MOCs to measure. I mean, in the natural 4-layer, because they're also stacked this antiferromagnetically, you have 2 antiferromagnet with 0 magnetization together, you get 0 plus 0, still 0. So I guess we've seen simple equation like 1 plus 1 stuff quite a few times in this conference. So here we do 0 plus 0, okay, even simpler. So again, this is all by this stack built twisted double bilayer chromium iodide. The main finding is, of course, 0 plus 0 is not 0 in this case. When you stack, then with the twist angle, you actually emerge a ferromagnet-like hysteresis loop response. In fact, this occurs in a very wide range of twist angle, pretty much as soon as start from about half degree also, all the way to 20 or 30 degrees. Sorry, 20 degrees, you have a emergent this hysteresis loop in this twisted. So there's no magic angle in the M4. Only in a very small angle or a very large angle, they seem to be decoupled. You don't see this. And, of course, everything when you apply an electrical device. So when you apply a gate voltage, and in fact, you can, so this is one of the devices. I show this emergency loop. You can park a magnetic field nearby and start applying gate voltage. You can drive this very interesting switches between different states by the voltage. So there's a lot of interesting magnetic electric effect. Not everything we actually understood. For example, the slope depends quite interestingly on the twisting angle, so on and so forth. Also, the temperature dependence is very interesting. So usual ferromagnet, when you raise temperature, you just kill the magnetic magnetization, right? So this twisted magnet, when you raise temperature, actually the magnetization goes up before it goes down eventually again. So indicating some interesting, perhaps multiple phases competing. And in fact, that is, there's quite already a fair bit amount of a theoretical prediction before people start to experiment experimentally. The main, long story short, is that when you twist the 2 magnets in this case, you start introducing this Mori pattern. As we all know, it's a spatial modulate stacking, or the way the lattices are aligned or registered to each other. So you actually no longer have a natural monolithic stacking, for example. You change it from monolithic to rhombohedral. And for this chromium iodide particularly, the interlayer exchange coupling, remember exchange still depends on wave function overlap, hopping, the so on and so forth. So when you twist them, you change this wave function overlap. In this case, you can actually modulate the interlayer spin exchange coupling from positive to negative, so you can alternate in between ferromagnetic region and antiferromagnetic region. So actually, so this is so-called the Mori magnetism is a form of very interesting non-collinear magnetism. Okay, so even more interestingly, so my colleague, theorist Pramit Upadhyaya in Purdue Electrical Engineering did a calculated phase diagram. So there's a number of different non-collinear phases all coexisting depending on the balance of the parameter between spin stiffness that makes each layer behave like ferromagnet, and the anisotropy that make them all the plane, and most importantly, a spatial-dependent interlayer exchange of coupling parameter. So depending how these work out, you can get a very interesting rich phase diagram. When you change twisting angle, so in the very small twist angle, the Moiré periodicity is very large. So the domain size is very large. So domain kind of wins. But when you reduce the twist angle, increase twist angle, the domain shrinks. Now domain wall becomes important. So there's competition between domain and domain wall energy. So there's actually favor different type of non-collinear phases or simply collinear phases if you don't want any. If you have lots of domain walls, you don't want any domain walls. And system actually become collinear. But for example, in the large periodicity, domain wins, then you want to listen to the local stacking the induced magnetic order. So some places it's a ferromagnet, some place antiferromagnet, but then you will make this intralayer chromium iodide unhappy, create these domain walls. So there's a different phases exist in this intro diagram. When you change temperature or voltage, you can actually traverse between different phases that can create a phenomenon like temporarily you get a stronger magnetization before it dies over. In fact, this is reproduced in the calculation. So I think this is a very interesting system. In fact, there's a lot of photonics experts here, so I like to pose a question. So this is system basically not only 0 plus 0 is non-zero, but basically you created this spatially modulated, almost periodic with sub-wavelength, sub-optical wavelength periodicity, 10 nanometer region between ferromagnetic region, antiferromagnetic region. The ferromagnetic region, of course, has the finite curve rotation to the linear polarization of light. The antiferromagnetic region has no curve rotation. So this reminds, at least me, some kind of metamaterial for magnetism. Of course, the conventional metamaterial or metasurface, we heard a lot of talk from experts, has this spatial modulation between, say, conductors or insulator or material with different dielectric property. Here is a spatial modulation in sub-wavelengths with a material with very different magnetic property. Does this system have interesting light interaction? I don't know. I'd like to pose this question. If you have ideas, let's discuss. Okay, at lunch or after beer, whatever. Okay, so I'm coming to the end. So just very quickly, you can also stack two different kind of antiferromagnet. This is stacking chromium iodide, which I just mentioned is a perpendicular interlayer antiferromagnet onto chromium chromide. I think we also heard yesterday is this in-plane antiferromagnet. Also, turns out it emerged a ferromagnetic state. But this is a different physics. This is more like exchange bias. So what happens, supported by defect calculation, is that this layer of a chromium iodide actually make its neighboring layer of chromium iodide more listen to itself. It actually rotated its anisotropy to be ferromagnetic coupled to this chromium iodide. So this interface emerged these ferromagnetic response. And yet, no surprise, again, we always build devices, we'll never do these measurements. So when you perform gating, you can show, because now you have these asymmetry, structure symmetry, you can actually enhance the magnetic-electric response. The electric tuning of the response is much stronger in this heterostructure compared to each individual material, which is consistent with a new kind of a magnetic coupling become available when you have this asymmetry that you can review in this gated MOC measurements. So I think that's the end. I hope I introduced several hopefully interesting examples that these multimodal operando measurements of different sort combined with device transport can reveal a lot of interesting physics about this very interesting 2D material, particularly Moiré systems. And I'm always very happy to explore collaboration with the colleagues. Thank you very much.
Okay, thank you for the overview of all these interesting experiments. Please, questions.
Yeah, it's interesting to see these mixed phases of ferromagnetic, antiferromagnetic phases, but do you first of all have direct evidence about the coexistence of these two phases spatially? That's one thing. Second thing is that are these special phase-separated regions, are they directly correlated to some kind of structural changes, like the ferromagnetic or antiferromagnetic regions? Are the structure somehow a little bit different, like the interlayer spacing or whatever?
Okay, thank you for your question. So I think first question is, right now we don't have a local magnetic probe to directly visualize the spatial, I think you mean spatial coexistence of a ferromagnetic domain. It's more of indirect evidence consistent with the model and calculation. Of course, our measurement is a micron size. However, we are talking to some, for example, scanning NV people to try to characterize these physics, or maybe other type of local probes. Second question is the structural. So we've done some For example, TEM images we show we form these Mori pattern with expected periodicity. We've also done some Raman imaging to show there's no obvious string pattern. So I think that's the two information I can point out. But of course, again, more local probes to see detailed structures is still interesting.
You need to do the TEM or the Raman at low temperature, right? Because at certain temperature, over the TC, then it's all the same, right? So it should be below the critical temperature, and then you see whether the FM or AFM, is corresponding to some different structures.
Yeah, good point. I totally agree. I think we have more. By the way, our Raman it can be done at was done at low temperature. TEM, of course, at room temperature. We don't have yet the capability to lower the temperature. But I definitely agree. We need more characterization, material characterization that can measure at low temperature to correspond to a lot of interesting physics in quantum materials. Absolutely.